Okay, any questions? Yep. Oh yeah, the question is, will I finish up the fitness proportional selection thing that I started at the end of the lecture last time? Well, actually I finished it last time, but unfortunately the machinery cut me off. So the classroom tech guy is watching for when this lecture starts, and he's going to extend the time so I don't have to cut this lecture into two pieces, two different videos. But anyway, we'll just start off with that if there's no other questions. Any other questions? Okay, so we were talking about the so-called standard genetic algorithm, and that's something I want to abbreviate that way just to save space and whatever. And we talked about the genetic operators, crossover and mutation, and each of these you're going to have an associated user choice parameter, probability of mutation, probability of crossover. I talked about how those things worked, different kinds of crossover, 1 point, 2 point, K point, uniform, etc. Okay, and we started just talking about various selection methods, and the idea here is that the big picture is that you have a population at time t, so big sort of selection picture. And by the way, the ones we talked about last time included various kinds of elitism, where you keep the top 6% or keep the top 10% and figure out the rest of the parents for the next generation by some other way of picking. Okay, but anyway, the big selection picture is like this. What you do is you have populations of size n that's fixed throughout the whole thing, and from P of t you select somehow n individuals, and these guys, these individuals you select, are going to be the parents for individuals in P of t plus 1. And how do they become those parents? You pair them up. So you pair them up. You apply genetic operators, crossover, mutation, and then from that you end up with 2 offspring for whatever each parental pair. And they make up the individuals in P of t plus 1. So those go right into P of t plus 1. And that's how it works. Okay, so at the end of class, or at least at the end of the video, I started talking about this thing called fitness proportional selection. So I want to pick up on that now. All right, so we've got this fitness function. And the fitness function for a standard genetic algorithm, we're always going to assume that f of any string is positive. And remember, we're using this f of a string instead of f of g of a string, just to save space, whatever. So we have our fitness function, and f of x is going to be a strictly positive thing for every string x. And remember, what these populations contain are going to be binary strings of length capital L, where L is fixed throughout. Okay? And so what we want to do is we want to select the parents in the following fashion. Okay, so we want to select parents as follows. What we're going to do is we're going to make n independent draws from P of t. So you make n independent draws, I'll put that word in quotes, from P of t. And what do we mean by independent draws? Each draw, you draw somebody from P of t, and then you think of throwing them back in, and for the next parental draw, you make another draw, and so on. So you make n of these, you generate n parents that way. And what you want is, for any x in P of t, so for any individual x in P of t, we want the probability that you pick x on any of these n independent draws, so prob that you pick x on a draw, we want that to be proportional to the fitness of x. So we want that to be equal to some C0, some constant C0 times f of x, where C0 is the same for every string. Okay. So you see what's going on here? You have your population P of t, and you want to draw individuals independently and draws from P of t. So you draw one, you look at it, you record it, that's one of your parents, throw that back in. You do that again, you do that again. Same probability distribution over individuals in P of t each time for these draws. And the probability that you pick any specific x has got to be proportional to the fitness of x. Now, I claim that this condition here, this condition of fitness proportionality, determines C0 completely. So, turns out that this description of the desideratum, namely, what we want to do here, this description determines C0. Okay. How? Why? Well, this is because we need the following to be true. We need to have the sum over all y in P of t, so y is a letter for a string here. We need the sum of the probability that you pick y on a draw. We need that to equal 1. Now, why is that the case? Any suggestions? Okay, this is kind of a reality check. I just want to make sure we're on the same page here. Probability background. Why do we need that last summation to equal 1? Okay, all right. Here's why. When you draw from P of t, you have to pick somebody, right? So, the sum of the probabilities that you pick given y's has to be 1, because one of those y's has to be picked every time you make a draw. There's no way of not drawing somebody. Okay, maybe I'm beating a dead horse here. Maybe you guys are at home like rolling your eyes. Why didn't he think we could answer that question? I just had the feeling that people were not going to do it. Sorry about that, guys, if I'm insulting you. But anyway, all right, so what does that mean? That means that the sum over y in P of t of C0 f of y is equal to 1, which means that C0 itself is equal to 1 over the sum of the fitnesses of all the strings in P of t. Okay. So the bottom line is, for fitness proportional selection, you're making these n independent parental draws from P of t. On any given draw, the probability that you pick x for any x in P of t is going to be this times the fitness of x. So bottom line, and I'm going to introduce a little bit of new notation here. For any x in P of t, the probability that you select x on a draw on a parental draw is, and here's the new notation, P sub SEL, P sub select of x. And that's going to be f of x divided by the sum of all the fitnesses of all the strings in P of t. Okay. All right. So that's fitness proportional selection. That's how you draw the parents for the next generation using that particular selection technique. And, by the way, all the early papers by Holland and a lot of the stuff in the book, chapter that you've already read, talks about fitness proportional selection. That, they say, well, let's suppose we do fitness proportional selection, blah, blah, blah. So this is what they're talking about. Okay? All right, then. Now, one thing I want to comment on here. Remember, last time I was talking about how, that having this exogenous fitness function in genetic algorithms kind of bleaches out the fact that, there's that real biological evolution, your fitness, whether you survive to reproduce, is an endogenously determined thing. How fit you are depends on, who else is in the population. And I sort of said, well, genetic algorithms, they have this exogenous fitness function. There's nothing like that in biological evolution. That's true. That's true. But I just want to point out that fitness proportional selection does give you an endogenous component to the selection process. Like, if you want to decide how probable it is that, say, X gets picked to be a parent for the next generation on a given parental draw, that doesn't just depend on the fitness of X, it depends on the fitness of who else is there in that population P of t, right? So if the population P of t just happens to contain a lot of low fitness individuals compared to the fitness of X, then P cell of X is going to be relatively high. See that? So there is some endogenous effect on selection probabilities here. So I just want to note that there is some endogenous. I was going to try to use a word like I did. I used it on the tape that got wiped off. The endogeneity. I'm not even sure if that's a word. Endogenousness. I didn't want to take a chance. So I'm just going to say there is some endogenous effect here on selection probability, like P cell X depends not just on f of X, but on f of Y's for all the other Y's in P of t. Nonetheless, this endogenous effect, what mediates that endogenous effect is an exogenous fitness function, and nothing like that arises in nature. So nonetheless, this effect, the effect, is mediated by an endogenous or exogenous. Did I say endogenous a minute ago? I think I did. An exogenous fitness function. And there's nothing like that in nature. So this is an example of one of those contrasts of things like GAs, these stripped down evolutionary computational things that are inspired, bio-inspired, evolution-inspired, how they simplify, how they throw away things for biological evolution. Okay, so anyway, now we understand fitness proportional selection. Let's ask a few questions. So You have P of t, you pick your n parents for next P of t plus 1. On any given draw, you know the probability of picking any x. So let's consider the following question. For an individual x in P of t, so here's a question. If x is in P of t, so x is one of those individuals who's eligible to be a parent for P of t plus 1, what is the expected number of times that x appears among the parents for P of t plus 1? And remember, these draws we're making according to fitness proportional selection just make parents. They don't make strings that go into P of t plus 1. They make the parents for those strings. They still have to have genetic operators performed on them. And here I want to be careful. I want to say if x is in P of t and is a specific individual. So here we regard x's that are copies of the same string, that are distinct copies of the same string, as distinct individuals. So I'm just going to put the word different in quotes here. So, or maybe I'll just put different and then individuals. How about that? All right, so if x is in P of t, what is the expected number of times that x appears among the parents of P of t plus 1? Well, we could calculate this in any number of ways, but there's a nice, clean way to do it. And I used to go over both ways of doing it, but I thought, this is not a probability course, so I'm just going to do it the clean way. So here's a clean way to do this. And I guess maybe this is just my opinion that this is a clean way to do it. Maybe you'll disagree with this. Clean way to do this. Okay. I'm making n draws, right? So I have draw k as k runs from 1 to n. So for each k, 1 less than or equal to k less than or equal to n, I'm going to let zk be a random variable. What is this random variable going to be? Zk is going to be equal to 1 if we pick, let's get first person about this. We're doing this together. If we pick x on draw k, and zk is equal to 0 if not. So if you took some other individual than x on draw k, zk is 0. If you pick x on draw k, zk is 1. Now, these guys, because the draws are independent, the zk's from 1 to n are actually independent random variables. But that turns out not to matter. We don't need to know that, but it's true. Okay. What is the expected value of zk? zk is a 0, 1, and by the way, those of you from last semester, like Samar, Scott, John, who else? Who else took probability last spring? Forget. Okay, well anyway, at least you. You remember this as what's called a Bernoulli random variable, right? A Bernoulli random variable is a 0, 1 random variable that takes on the probability 1, or it takes on the value 1 with probability little p for some p. In this case, the little p is p cell of x because zk is 1. So note that the probability that zk is equal to 1 is p cell of x, the probability that I select x on any given draw, probability that zk equals 0 is 1 minus that, and this is true for all k, thus the expected value of zk is equal to 1 times p cell of x plus 0 times 1 minus p cell of x, which is equal to just p cell of x. Okay? That's the expected value of a Bernoulli p cell of x random variable. Meanwhile, the sum of the zk's from k equals 1 to n, sum from k equals 1 to n of the zk's, this is what? What is an easy way to describe that? It's a random variable, right? Like it takes on different values depending on your draws, but what is this value? What is the sum of the zk's? When zk is 1 when you pick x and 0 otherwise. Yes, it's the number of times you pick x. So this is the number of times, appearances, whatever, of x among the parents for the next generation. And thus the expected value of this is the expected number of x appearances among the parents. And that's what we were looking to calculate. That's what the Q was about up there, or Qn, or whatever you want to call it. So thus, expected value of the sum from k equals 1 to n of zk is equal to the expected number of x appearances among the parents. Okay? For p of t plus 1. And this is, by this calculation here, this is equal to n times p cell of x. Now, what is n times p cell of x? We have a formula for p cell of x. So that's n times f of x over the sum of all the fitnesses of all the strings in p of t. Now, I'm going to do something that the book does, which is rewrite this last thing as follows. I'll take that n in front there and put it in the denominator as a 1 over n. So it follows that, while I'm going to do this, you'll see why in a second, that the expected number of x appearances among the parents, p of t plus 1 parents, equals f of x divided by 1 over n times the sum of all the y's in p of t, f of 1. Okay, now why did we do that? Numerator is the fitness of x. Denominator is what? It's just the arithmetic mean, the average of the fitnesses of all strings in p of t. So the denominator here is equal to the numerical average, however you want to talk about it, numerical average fitness of a string in the population of time t. So how does one interpret this equation, this identity here, that the expected number of x occurrences for any individual x in P of t is the ratio of f of x to the average fitness? It says the following. It says that I live in mortal terror of, well, not mortal terror, but a kind of modified mortal terror of committing a blackboard error where there's an empty room and no one's here to say, Tristan, you're not here to say, no, stop, blackboards, whatever. So I told that to my other class yesterday. I was giving a lecture for that class in here yesterday. And just like you guys, they had nothing. They didn't respond. So anyway, I wasn't surprised. Don't worry, I'm not going crazy. Well, maybe I am. Who knows? This says that if a given individual, and I'm going to try to say this all in words without using equation. If a given individual in the population time t, okay, I lied, I'm going to write P of t. A given individual in P of t has above average fitness and when I say above average fitness, that's an endogenously determined thing. Above average fitness relative to everybody else in P of t. So relative to P of t. So if a given individual has above average fitness, you expect that individual to appear at least once among the parents for P of t plus 1. So this feels good. This feels, evolutionarily good. That if you're an above average fitness relative to everybody else who's there, then you are probably, or we expect to see you at least once among the parents. You're not liable to get selected out, so to speak. Okay. All right. So that's one thing, and that looks promising. Looks like we're going in the right direction here. So let's see if we can take it a step further. Suppose there are, say, m copies of the same string in the population at time t. So let's say take this a step further. What if P of t contains m copies of some string? Okay. Now remember, I'm thinking of, when I did all this calculation about expected number of times an individual appears in the list of parents for P of t plus 1, I regarded copies of the same string that appear in population of P of t as different individuals. So now I'm going to think a little differently here. I'm going to ask, given this is true, given P of t contains m copies of some specific string, what is going to be the expected number of times that string appears among the parents for P of t plus 1? So what is the expected number of times that string appears among the P of t plus 1 parent list? Okay. What is that going to be? Well, I claim it's just going to be m times the expected number of times that any one of those individual representatives of that string appears. Because, say, let's give that string a name. Let's call that string theta. So let's call the string theta. And that's a little bit of a deviation from our usual lower Roman letter convention for strings. And I claim that the expected number of theta appearances is going to be equal to the sum over all x in P of t, such that, and these are different individuals where x is an instance of theta, of the expected number of x appearances among those parents. Now, every x that's an instance of theta has the same fitness f of x, so this number here, this being summed, this is the same for every term in the sum. And that's going to just be this. It's going to be k, or sorry, m times, because there's m of these, m x's represent theta in population at time t, times the expected value we just calculated a minute ago, which was, where is it? There. F of x divided by 1 over n times the sum over all y's, p of t, f of y. And let's write it this way. So if there's m reps of some specific string in the population at time t, the expected number of reps of that specific string in the population at time t plus 1 is going to be this quantity here. What does that say in words? Let's recast the little sentence at the top of the board over there to fit this. So this says that if a string has above average fitness relative to P of t, and I better say a string represented in P of t, if a string represented in P of t has above average fitness relative to P of t, then you expect to see among the parents for P of t plus 1 at least as many of those strings as were in P of t. So at least as many of that string as you had, or as you have in P of t. So if you have m reps of that string in P of t, and that string has above average fitness, then the expected number of times you see that string in the next population is going to be m times a quantity in brackets, which is bigger than 1, when f of x is bigger than relative to, is above average relative to P of t. Okay? So these are all promising things so far, that you know, as you select parents by fitness proportional selection, then things that are relatively more fit tend to proliferate in the sense that, you know, you expect to see more of them in the parental list, and once they're in the parental list, depending on the genetic operators, you know, they might give rise to things that look like them, you know, so traits will, you know, get selected for, whatever. You know, so all this stuff feels really good so far. Now you can generalize this. You can generalize this whole discussion here. So this is one step further. This generalizes, this kind of calculation generalizes to arbitrary subsets of P of T. What do I mean by that? Okay, well, I have this thing that I call, and by the way, you're going to get a handout on this whole schema discussion, which is where we're headed here. I'm not sure, you might already have seen it depending on when you're watching this lecture, but anyway, this kind of calculation generalizes to arbitrary subsets of P of T in the following sense. So I'm going to let Q be a subset of P of T. Okay? So Q is going to have some number of entries, or some number of individuals in it, and they might be different. They're not necessarily, m instances of the same string. They're not necessarily just a single string or the set consisting of a single string. So what turns out to be the case here? What turns out to be the case? The expected value, and I'm going to call this thing the subset selection lemma. Okay, a glorious term. I made that up. Okay, this is my theorem, so I have a right to name it the way I want, even if it's hokey, corny, whatever you want to call it. Subset selection lemma says the following, that in this context, the expected number of appearances of members of Q among the P of T plus 1 parent list equals this. Equals, and there's various ways of writing this. It's going to be equal to the sum over, let's say y, and let's use another. I'm not sure how I want to do this. I want to do it as clean as possible, as cleanly as possible here, so that it's. Let's just do y's. So it's the sum over y and q of the expected number of appearances of y among the parents for population at time t plus 1, which is going to be f of y divided by the sum over y in P of T of f of y. Okay? Now, you play around with this a little bit, and this is what comes up here. Let's write this let's continue this equality here. In the numerator, you're going to have sum over y and q of f of y. In the denominator, you're going to have sum over y and P of T of f of y. And if we write this as, in turn, first let this equal number of individuals in Q. So that's just the number of total individuals in the set Q. This is the same as Q, number of Q, times, in the numerator, I'm going to put 1 over Q, sum y in Q of f of y. And in the denominator, there's a missing n here somehow. Let's see. Oh yeah, there should be an n. There should be an n here. 1 over n here. So there's a 1 over n here. And now I have 1 over n times the sum y in p of t, f of y. And I'll put that quantity in brackets. Okay. Did everybody get the 1 over n? This was missing earlier. Okay. So what does this say? Let's put this in words. What is the numerator of the bracketed term? It's the arithmetic mean of all the fitnesses of guys in Q. What is the denominator? It's the arithmetic mean of all the fitnesses of all the guys in the whole population. This number of elements of Q sitting on the outside times that, what does this say? This says that for any subset Q of P of T, of P of T, if the average fitness of guys in Q is higher than the average fitness of the guys in the whole population. So if average fitness of Q members is bigger than the average fitness of members of the whole P of T, of everyone in P of T, we expect, and I'm always using the word expect in these word expect, you know, expected value is what I'm thinking here. We expect to see more than number of guys in Q, members of Q, or representatives, more than number of Q, individuals from Q, among the P of T plus 1 parents. In other words, high average fitness subsets of P of T proliferate in the sense that you see more of them among the parents for P of T plus 1 than you saw in P of T. So, in loose words, high average fitness Qs tend to, and I have to use single quotes because now we have an embedded quotation, tend to proliferate. Proliferate. In some sense. Okay, so all these things are things that Holland calculated first and did all these calculations, and his whole approach to understanding the way GAs worked started with these calculations and applied them in a special case, a special kind of a Q. Okay. So these are, by the way, these are rigorous. Well, everything we've done so far is rigorous. These rigorous calculations sort of inspired Holland and his cohorts, or cohort, I guess, I don't know what you're going to say, his buddies, so let's say Holland et al. How about that? Is that fair enough? So, inspired Holland et al. To develop a sort of a heuristic. Remember, these are rigorous calculations, but they developed a kind of a candidate, a proposed, I'll put in quotes, proposed rationale for how the SGA operates and why we expect it to do well. in finding good problem solutions. So how the SGA operates, and the analysis they did was based on the idea of a schema. We'll get to that. And essentially, what they did was they applied the subset selection lemma to a special lemma, gotta learn how to spell, to a specific Q. Okay, so what is Q? What a specific kind of Q they looked at. And Q is going to be what I'll call H intersect P of T. So a specific Q type. Q equals H intersect P of T, where H is a schema. Okay, so now we finally encounter the word schema. And if you were here, we would take the 3-minute break right about now. Actually, we would have taken it about 5 minutes ago, but anyway. You know, I really hope this is recording. That's one of those things. You don't want to have to give a whole lecture over again. 15 minutes, fine. Okay, so how many people are in the Eastern time zone? Daylight time. Okay, how many people? Does everyone know that Arizona doesn't do daylight time? Who's from Arizona? Nobody? Okay, Arizona is always on Mountain Standard Time. So what that means is that at some times of year, they are the same time as Colorado, and at other times they are an hour. What is it? Earlier in Colorado on their clocks. See, I'm just wasting the 3-minute break here because there's no questions. You know, the empty chairs, I just gonna let my mind wander. But like I say, the breaks are for me as much as they are for you. So grant me that license. Okay, so let's get back to this. Subset selection lemma. And you know, I could have turned off the camera and pretended that I wasn't talking to myself, and then you wouldn't have thought I was crazy, but I decided not to. I decided to let you see the naked truth. Okay, so subset selection lemma says that. Now, what is a schema? You all know what a schema is. You've played with schemas, and you know, you can call them, by the way, the official plural for the word schema is not schemas, it's schemata. So if you want to go around saying schemata, that's fine. But people will kind of giggle behind your back and talk about, oh my God, I can't even. Schemata, whatever. Anyway, so what's a schema? So recall that you can think of a schema either as a set of strings, and that's how I'm thinking of it here, because I'm writing it set of strings or multi-set of strings intersect other set of strings. So a set of strings, as in this H above, or in terms of its defining symbol. And symbol. What is the defining symbol of a schema? This is going to be an L tuple. So if you're talking about L-bit strings, the symbols are going to be L tuples of 0, 1, and star. Okay? So let's just what the heck? Let's say, how about if, say, L equals 3? Then the symbol, this star 1 star, represents, this is the symbol, and what set of strings does that represent? It represents the set of strings I get when I put whatever I want as the two stars. So 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. Okay. Everybody know how that works? Cool. Okay. Here's the set. Here's the symbol. All right, now H is the letter everybody uses for a schema. Okay, does anyone know, and I don't think the book even tells us this, does anyone know why we use H? Okay, and let's see if you can come up with this. Any OR majors in the room? Okay. All right. All right, so let's look at this schema here. This is, in some sense, the set of all 3 tuples of 0, 1 stars such that the middle one equals 1. What if I look in, say, Rn, and I talk about the set of all points in Rn such that x3 equals 1, or x3 equals 0? What kind of a set is that in Rn? Okay, I give up. Scott. Yes, that's right. And I really hope you got it. Hyperplane. H is why, that's why we use H for schema. So the letter H, at least this is my opinion. This has never been confirmed by Holland or anybody associated with him. The letter H sort of stands for hyperplane, because you can think of these things, can think of a schema with literally one defining symbol as a hyperplane in the set of all binary strings of length L, or one star symbol, I should say, or one defined symbol as a hyperplane in the set of all L strings. All right, if a schema has only one defined symbol, or fixed position, fixed bit, so this is an example of such a thing, then it's literally a hyperplane in binary L tuple space. I mean literally in the literal sense, not in the modern day kid sense of, oh man, I was literally totally blown away by that. Anyway, literally a hyperplane in binary L tuple space. And something with more than one fixed bit is sort of a lower dimensional hyperplane. So when you define more than one, you get lower dimensional. I'll put that in quotes. And only the math kids in the room, need to worry about this or think about it or might be interested. But these are hyperplane-like objects. All right. So anyway, I just spent 5 minutes talking about why we call schemas H. Is that a waste of my time or your time or both? I don't think so. I think it's fun. Okay. So anyway, Holland applied the subset selection lemma as best he could to certain special subsets of P of T. Now, why did they do that? Why did he do that? Basically, he came up with this thing called the Schema Theorem. And the Schema Theorem is really a kind of a direct application of the subset selection lemma along with some other stuff. And he said, this is why genetic algorithms work the way they do. And it turns out that's not the case. And to understand that, what I want to do is I want to back off and I want to talk about like what the kind of the background thinking was that underlay Holland's view of the way genetic algorithms worked. Okay, so some background. And a lot of this comes with flowery language that Holland made up and that others have made fun of over the years. But anyway, some background. So you look at biological evolution. So in biological evolution, what we see, genetically at least, at the genome level, is you see parts of the genome that encode for proteins. And you also see parts of the genome that control other things. But let's just think about the ones that encode for proteins, right? Now, how do they encode for proteins? Like I mentioned earlier in the course, it doesn't even have to be a sequential part of the genome, but often it is. And how does it encode for proteins? Well, base pair triples encode for amino acids. The amino acids string together into polypeptide chains to make proteins. So, for example, like hemoglobin has 143 amino acids. You know, I think that's the way it works. But anyway, pieces of the genome encode for proteins. And when a sexually reproducing species reproduces, what happens is that, you know, the chromosomes go through this weird dance where they cross over with each other in various places. And so you think that like parts of the genome that are close together to each other, right, are going to be less likely to be screwed up by this cutting and pasting and crossing over process than parts that are far apart. So what you see, you often see the following phenomenon. You often see little important short segments of the genome that are just sitting there that kind of persist, that usually persist. And when I say important, I mean like they encode for an important protein or something like that. That persist generation to generation through crossover and the mutation processes that go along with the gamma. Remember, capital gamma are biological genetic operators. So I'll put that in quotes, the gamma process. Okay? And so Holland was thinking, well, maybe you know, if we have these bit strings that encode problem solutions, then they're going to be like short, important pieces of these binary strings of length L that encode for features of a good problem solution. Just like this would encode, you know, short genome sequence that persists through crossover mutation might encode for features of a successful individual, like, for example, encoding for hemoglobin, right? You need hemoglobin. So, anyway, Holland wanted to get to the crux of how GAs might work by way of this kind of thinking. So Holland sort of ported this kind of observation to GAs by means of what has come to be known as the building, he called it the building block hypothesis. And later on, why did I leave the space here? The people who debunked the Schema Theorem and explained, you know, that why it wasn't the way genetic algorithms work, renamed it the static building block hypothesis, and you'll see why as we go along. Okay, so the static building block hypothesis. What was that? For Holland, a building block to Holland was a high average fitness schema. So it's a schema with the following properties. it has high average fitness. And remember, what is average fitness? What does high mean? That's a relative concept. Depends on P of t, but for now, we're just going to leave it out. Has high average fitness. Has relatively few defined bits, fixed bits. And a relatively short, what we call defining length. Okay, so what is the defining length of a schema? What is the defining length of a schema? It's the distance between, so roughly speaking, this is the quote-unquote distance between the most widely separated pair of defined bits, fixed bits. I'll do an example in a second. So, for example, this schema, say star 1, star 0, star, let's make a 8 bits thing. Okay, so that schema. All right, what is the defining length of that schema? It's the distance between here and here. So what is the idea of if you have a short defining length versus a long defining length? Short defining length schemas are less likely to get destroyed by one-point crossover, because how might such a thing get destroyed by one-point crossover? Well, say you have two parents that are paired up. One of the parents is an instance of this schema, and the other parent is not. If you cross them over and the crossover point happens to fall in this defining length zone, then, boom, suddenly neither of the offspring is representative of that schema. Okay? So, relatively few fixed bits is another thing that is good for getting preserved by things like mutation and crossover, and the high average fitness. Okay, so the idea here is that if you have a short defining length, then crossover is less likely to quote-unquote destroy you, at least in terms of representing that schema. So in the sense that at least one of the offspring of a crossover is more likely to still be in the schema. But anyway, sometimes I wonder even why I go over this stuff. I think it's important because it's wishful thinking on the part of the people who developed this theory. They really, really wanted GAs to work kind of like biological evolution in the sense, that there's these short pieces of DNA that are important and somehow they get preserved, and we're going to use this to drive optimization, whatever. And the static building block hypothesis, now that we know what a building block is, static building block hypothesis says the following: that when you run a GA, so the static, I'll put that in parentheses still, building block hypothesis says that as you run a GA, what happens when you're running a GA? In effect, you're pitting pitting one building block against another. And the building blocks, or you're pitting one schema against another. And in fact, you're not just pitting one schema against another, you're pitting a whole bunch of pairs of schemas against each other. So in parallel, so in effect you are in parallel comparing fitnesses of lots of schemas. And when I say fitness of a schema, I mean like the average fitness of the strings in the schema, right? And so what happens, so he called this whole process, like I said, there's a lot of flowery terminology here, building blocks. Well, that's kind of unimaginative, but he called this is a lot more mysterious, implicit parallelism. Okay, that totally floats my boat in terms of floweriness. So you're comparing fitnesses of lots of schemas, and the ones that last over time are going to be what? They're going to be the ones that have relatively high average fitness, okay, because they're more likely to be selected on a fitness basis. And they're also going to be the ones that are less likely to get destroyed during the genetic operations, because even if you have a representative of a very high fitness schema and it gets selected to be a parent, if it's got a big defining length, then for all you know, neither offspring is going to be instance of that schema. And relatively few defined bits means that mutation is not going to screw you up. Okay, mutation will not screw you up. The ones that last over time are precisely the building blocks. And what happens is that as you run the algorithm, keep running the algorithm, the population is going to feature lots of individuals who are members of building blocks. And so the building blocks are in some sense going to be pieced together. The intersection of two schemas is a schema. We know that. So you have one building block intersecting another. That gives you a great thing if they're both very high fitness, whatever. That's his rationale. Okay. So they join forces. I'll put that in quotes, i.e. intersect. And high fitness individuals that you develop over time you can think of them as being built up from these building blocks. They are instances of all the different high fitness schemas that got selected in this implicit parallelism process. So they instantiate building blocks. Okay, so that's where he was going with this static building block, this building block hypothesis. That how a GA worked is that by over time, what happens is that high average fitness schemas with relatively few defined bits and a relatively short defining length proliferate. And that's what's going to happen. And the theorem he quote unquote proved, which is, by the way, not only is it a really weak theorem, but it's the proof in the book, which is the same as the original one that Holland gave, is not rigorous. So basically, what I did was I came up with a rigorous proof, okay? And in the course of coming up with the rigorous proof, I actually proved a stronger theorem, a slightly stronger theorem. So that's what's in the handout you're going to see shortly. But what is the schema theorem? The schema theorem gives you, it uses the rigorous math, the rigorous sort of Q math that we've been talking about today. So the schema theorem uses, which is based on the quote-unquote Q math, we've discussed today. Today is one word. Applied to Q equals H intersect P of T, where H is a schema. What does the schema theorem do? It puts a lower bound, and it's a weak lower bound on the expected number of H representative or QH representatives in P of T plus 1's parents, so among P of T plus 1 parents, and that lower bound is based on the number of guys in H intersect P of T, the defining length of H, the average fitness of H, and I want to emphasize here that the average fitness of the individuals in H intersect P of T, and the number of defined bits. In H. All right, now, there's nothing wrong with the schema theorem. Whenever I say this, I feel like, you know, those Seinfeld episodes. Seinfeld is probably too old for you guys, but Seinfeld, whenever he would often say, like, about something, well, not that there's anything wrong with that, but, you know, that was one of his favorite things, and that's how I feel when I say there's nothing wrong with the schema theorem. It's just not very useful, okay, unfortunately. And part of, you know, the reason the proof in the book isn't rigorous is because they mix up, they conflate expected values and actual numbers in a really weird way, blah, blah, blah. But whatever, it turns out that this does not explain the way genetic algorithms operate. And so what I want to do is next time I want to pick up here and talk about some examples from the literature, some early and more recent examples that give you an intuition for why this shouldn't explain the way genetic algorithms work, and then we'll move on to analyze them in the only rigorous way possible, which is as Markov chains on population space. So we will hope you're doing okay, and I'll see you soon.